On the 10th of April, 2019, images began appearing on screens around the world, and physicists, for just a moment, stopped breathing. It was blurry, orange, asymmetrical. It looked almost like an eye, a dark center surrounded by a ring of fire. And it was the first photograph of a black hole ever taken in human history. The object in that image was M87, a black hole 6.5 billion times the mass of our Sunday 55 million light-years away. To resolve it, the team had connected 8 radio telescopes spread across 4 continents. They had essentially turned the entire planet Earth into one enormous antenna. The world celebrated. Scientists wept. It made headlines everywhere. But in the days that followed, there was something almost no one talked about. This image didn't just confirm that black holes exist. It revealed something deeply, fundamentally strange about the physics happening at that boundary, the threshold where everything we know about space, time, and matter stops working. And 3 years later, when they imaged our own galaxy's black hole, Sagittarius A, for the first time, the strangeness deepened further. Because what they found at the center of the Milky Way did not behave the way any model had predicted. This is the story of what happens when you look directly into a black hole, what we learned, what it broke, and why it matters far beyond the walls of any physics department. Everyone thought they knew what a black hole was. A region of space where gravity is so strong that nothing can escape, not matter, not light, nothing. That part was correct. But the image most people carry in their minds, something like a drain, a hole in space sucking things in, is wrong in ways that matter. A black hole is not a hole. It is an object, an extraordinarily dense object. More precisely, it is the result of so much mass compressed into such a small volume that the escape velocity, the speed required to break free from its gravitational pull, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can escape. The boundary where this happens has a name, the event horizon. It is not a physical surface. There is no wall there, no membrane, nothing you could touch. It is simply a point of no return, a threshold. Cross it, and you are gone. Not because something grabbed you, but because every path forward through space, every direction you could possibly go now, leads deeper inward. The geometry of space-time itself has curved past the point of return. And this is where things get strange. Because general relativity tells us what happens at and beyond the event horizon, and it is something human intuition is entirely unprepared to process. Einstein published his general theory of relativity in 1915. He replaced Newton's description of gravity, a force acting between masses across empty space, with something far more radical. Gravity, Einstein said, is not a force. It is the curvature of space-time itself. Mass warps the fabric of the universe around it. Other objects follow the curves in that fabric. What we experience as gravitational attraction is actually objects taking the straightest possible path through curved space. This was confirmed spectacularly in 1919, when astronomers observed starlight bending around the sun during a solar eclipse, exactly as Einstein's equations predicted. The world declared him a genius. Newton, as with everything in science, wasn't wrong, he was just incomplete. But Einstein's equations also produced a result that made even Einstein uncomfortable. Karl Schwarzschild, a German physicist serving on the Russian front during World War I, solved Einstein's equations for a perfectly spherical, non-rotating mass in 1916. He sent the solution to Einstein from the trenches. And embedded in that solution was something Einstein initially refused to believe. At a certain radius around a sufficiently massive object, now called the Schwarzschild radius, the equations broke down. They produced infinities, divisions by zero, results with no physical meaning. Schwarzschild died a few months later from an illness contracted at the front. He never saw what his solution ultimately implied. It implied that black holes were real. Einstein spent years arguing they couldn't actually form in nature, that some physical process would always intervene to prevent it. He was wrong. We now know that when a star of sufficient mass exhausts its nuclear fuel, the outward pressure that had been balancing gravity disappears. The core collapses. In milliseconds, what was a stellar core becomes a singularity, a point of infinite density surrounded by an event horizon. A black hole is born, and the equations that describe what happens at and beyond the event horizon contain some of the most disturbing predictions in all of physics. Here is what general relativity says happens as you approach a black hole. Time slows down. Not metaphorically, not as a figure of speech. Literally, physically, measurably, time passes more slowly in stronger gravitational fields. This is called gravitational time dilation, and it is not a theoretical curiosity. It has been experimentally confirmed. GPS satellites orbiting at altitudes where gravity is slightly weaker than at Earth's surface run their clocks slightly faster than clocks on the ground. Engineers have to correct for this difference every single day. Without Einstein's correction, GPS would accumulate errors of several kilometers within hours, and the system would be completely useless. Near a black hole, this effect becomes extreme. If you were watching someone fall toward the event horizon from a safe distance, you would see them slow down. Their movements would become sluggish. Their light would redshift, stretching toward longer, redder wavelengths as photons struggled to climb out of the gravitational well. Eventually, they would appear to freeze at the edge of the event horizon for what would seem, from your perspective, like an eternity. They would never appear to cross it. But from the perspective of the person falling in, assuming they survive the approach, something completely different would happen. They would cross the event horizon without noticing anything special. No wall, no alarm, no dramatic flash of light, just an invisible, unmarked threshold beyond which return is impossible. And if the black hole were massive enough, they could survive for hours or even days of subjective time inside the event horizon before reaching the singularity. Inside, the equations of general relativity predict something that has no equivalent in everyday experience. The direction of time becomes the direction toward the singularity, not a metaphor. In normal space, you can choose to move in any spatial direction, but cannot choose to move backward in time in the same way. Inside a black hole's event horizon, you cannot choose to move away from the singularity. It is not a place you can avoid. It is a moment in time that is coming for you. Every path through space-time, every possible future, leads to the singularity. You cannot avoid it for the same reason you cannot avoid next Tuesday. But this is where the story gets genuinely strange. Because the singularity, that point of infinite density at the center, is not actually something physicists believe exists in reality. It is a symptom of a broken theory. When a physical theory produces an infinity, it is almost always telling you that the theory has been pushed outside the domain where it applies. Newton's mechanics produced infinities at very high speeds, speeds approaching light, and those infinities were resolved when Einstein's relativity replaced it at those scales. General relativity produces an infinity at the singularity. This tells physicists that general relativity, the most precisely tested theory in the history of physics, breaks down at that point. Something else, some deeper theory we don't yet have, must take over. That theory would almost certainly involve quantum mechanics, the physics of the very small. And this is the central crisis at the heart of modern physics. General relativity describes the very large brilliantly. Quantum mechanics describes the very small brilliantly. The two have never been successfully unified into a single framework. And nowhere in the universe does that unification matter more than at the singularity of a black hole, where stellar mass has been compressed into the very small. We need a theory of quantum gravity. We don't have one. And the more carefully we look at black holes, the more visible that gap becomes. On the 12th of May, 2022, the Event Horizon Telescope collaboration published the first image of Sagittarius A, our own galaxy's central black hole. Approximately 4 million times the mass of our Sunday 26,000 light-years from Earth, near the center of the Milky Way, and never directly imaged before. The technical achievement required to produce that image is almost beyond description. Radio telescopes across multiple continents in Chile, Hawaii, Arizona, Spain, Greenland, Antarctica were synchronized to observe simultaneously. The data they collected was so vast, it could not be transmitted over any network. It was stored on hard drives and physically flown to a processing center in Massachusetts. The equivalent of synchronizing the ticking of clocks spread across the entire planet to within a fraction of a trillionth of a second. And when the image appeared, it looked familiar, a dark shadow surrounded by a glowing ring of plasma. But it was also different from M87 times in ways that immediately puzzled scientists. Sagittarius A times is about 1,500 times less massive than M87. Because of this, matter orbits it much faster. Where material takes days or weeks to orbit M87, it takes only
minutes to orbit Sagittarius A. This meant that during the observation period, which spanned several nights, the environment around Sagittarius A times was changing faster than the telescopes could capture it. The image was like trying to photograph a spinning top with a camera set to a very long exposure. The result was a blurred composite, a time-averaged snapshot of something that was churning and flickering throughout the entire observation. And in that churning, scientists saw behavior they did not expect. The plasma around the black hole was not distributed evenly. There were hotspots, regions of intense brightness appearing to orbit the black hole at extraordinary speeds. Speeds approaching a significant fraction of the speed of light. In the years that followed, a team operating the gravity instrument at the Very Large Telescope in Chile tracked individual flares of emission near Sagittarius A times, using a technique called near-infrared interferometry. Flares apparently produced by hotspots of plasma orbiting at roughly 30% of the speed of light, at a distance of only a few times the event horizon radius. The orbital period of these hotspots, approximately 45 minutes. To complete one full orbit around our galaxy's central black hole in 45 minutes, plasma must be moving at speeds that would be unimaginable in any other context. And critically, these hotspots did not behave the way the simplest models predicted. The behavior of matter near black holes is described by a set of models grouped under the term magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields. Near a black hole, the plasma falling inward carries magnetic field lines with it. Those field lines become compressed, twisted, and amplified as the plasma spirals inward. Under the right conditions, those tangled magnetic fields can snap and reconnect, a process called magnetic reconnection, releasing enormous amounts of energy in a very short time. This is believed to be the mechanism behind the flares seen near Sagittarius A. But the details of how those flares evolve, how the hotspots form and dissipate, how the magnetic field geometry behaves in the extreme curvature near the event horizon, none of it matched the predictions of the simplest models cleanly. The plasma was more turbulent than expected. The magnetic field behavior was more complex. The flares occurred on timescales that existing simulations struggled to reproduce. This is not a failure of the theory in the dramatic sense of the theory being wrong. It is something more subtle and in some ways more interesting. It is the theory revealing its own incompleteness. And then there is the information paradox. This is perhaps the deepest problem black holes have posed to physics, and it has resisted solution for nearly 50 years. In 1974, Stephen Hawking applied quantum mechanical principles to the region just outside the event horizon and discovered something astonishing. Black holes are not entirely black. Quantum mechanics tells us that empty space is not truly empty. At the smallest scales, pairs of particles constantly pop into existence and annihilate each other, a phenomenon called quantum fluctuation. Normally, these pairs appear and disappear too quickly to have any macroscopic effect. But at the event horizon of a black hole, something different can happen. A pair of particles can appear at the boundary, with one falling inward past the event horizon and the other escaping outward into space. The escaping particle carries energy. That energy has to come from somewhere, and according to Hawking's calculation, it comes from the black hole itself. The black hole very slowly loses mass. It very slowly radiates. This radiation is now called Hawking radiation. For stellar mass black holes, the temperature of this radiation is so fantastically low, far colder than the cosmic microwave background radiation that fills the universe, that it is completely undetectable with any instrument we currently have. But the implications are profound. If a black hole slowly radiates energy, it slowly loses mass. Given enough time, incomprehensibly vast amounts of time, it could eventually evaporate entirely. And here is the problem. Quantum mechanics has a fundamental rule. Information cannot be destroyed. The quantum state of any system, all the information about what it is made of, how it is arranged, what its history is, must be conserved. It can be scrambled, transformed, made practically inaccessible, but it cannot simply cease to exist. So when a black hole evaporates, what happens to all the information about everything that ever fell into it? If Hawking radiation is truly random, truly thermal, containing no information about what fell in then when the black hole is gone, that information is gone too. This would violate one of the most fundamental principles of quantum mechanics. Either Hawking radiation carries information somehow, and we don't understand how, or information really is destroyed, and we need to rewrite quantum mechanics, or there is something else happening that we haven't thought of yet. This is the black hole information paradox.
Hawking spent decades working on it. Stephen Hawking, Juan Maldacena, Leonard Susskind, Andrew Strominger, and many others devoted enormous portions of their careers to it. In 2004, Hawking conceded at a conference in Dublin that he believed information was not destroyed, that it escaped somehow encoded in the Hawking radiation, and paid off a bet he had made years earlier. But the mechanism by which this happens remains one of the deepest open questions in theoretical physics. The answer, when it comes, will almost certainly require exactly the unified theory of quantum gravity that the singularity also demands. Black holes are not just extreme astrophysical objects. They are the universe's way of telling us that our two best theories of physical reality are fundamentally incomplete. Step back for a moment and think about why this matters beyond the equations. The universe is full of black holes. Stellar mass black holes, the remnants of collapsed stars, are scattered throughout every galaxy. Our own Milky Way is estimated to contain tens of millions of them. Most are invisible, detectable only when they interact with a companion star and produce X-rays as they pull material off it. Supermassive black holes, millions to billions of times the mass of the Sun, appear to sit at the centers of nearly every large galaxy, including ours, including M87, including the galaxies we see at the edge of the observable universe. And there is a fact that took astronomers decades to fully absorb. Supermassive black holes grew up alongside their galaxies. The mass of the supermassive black hole at the center of a galaxy is tightly correlated with the mass of the galaxy's central bulge, the dense sphere of old stars at the galaxy's heart. This correlation holds across an enormous range of galaxy sizes and types. This means that black holes and galaxies did not develop independently. They co-evolved. They influenced each other. The black hole's growth affected the galaxy. The galaxy's evolution affected the black hole. When a supermassive black hole is actively feeding, drawing in enormous quantities of gas and dust, generating the brilliant radiation of a quasar or active galactic nucleus, it can launch jets of plasma at nearly the speed of light, extending for millions of light years in either direction. These jets heat the surrounding gas of the galaxy, preventing it from cooling and collapsing into new stars. The black hole, in effect, regulates the star formation rate of its entire host galaxy. This is one of the most surprising discoveries of modern astronomy. The largest structures in the universe, galaxies containing hundreds of billions of stars, are in some sense shaped by what happens in a region barely larger than our own solar system at their centers. The behavior of black holes is not just a matter of theoretical physics. It is, in a very real sense, why the universe looks the way it does. There is one more thing worth understanding. The first image of a black hole in 2019 was not just a scientific result, it was a proof of concept. A demonstration that the Event Horizon Telescope, this network of synchronized observatories spanning the planet, could actually do what it set out to do. Since then, the collaboration has been working on something more ambitious. Not just a static image, a movie. By combining observations across multiple years and improving the computational techniques used to reconstruct images from raw telescope data, the goal is to produce something that has never existed before. A time-resolved view of how the plasma, magnetic fields, and hotspots near the event horizon of Sagittarius A times actually evolve over minutes and hours. Not a photograph of a black hole. A film. When that becomes possible, and the technical progress of recent years suggests it is becoming possible,
from the elegance of Einstein's equations through the first detection of gravitational waves, we finally arrive at the first true image of a black hole.
We will be able to watch the physics break. And perhaps, in watching it break precisely enough, we will finally understand what comes next. Throughout all of human history, black holes were theoretical. Mathematical solutions to equations, predictions that many physicists doubted would ever be confirmed in nature. Then we confirmed them, then we imaged them. Then we watched plasma orbit one in our own backyard at a third of the speed of light. And each time we looked more carefully, the universe gave us not answers, but better questions. The singularity that breaks general relativity. The information paradox that breaks quantum mechanics. The coevolution of black holes and galaxies that we still don't fully understand. The magnetic field behavior near the event horizon that our best simulations cannot fully reproduce. These are not failures of science. They are science working exactly as it is supposed to work. We built the tools to see something we had never seen before. We looked, and the universe turned out to be stranger, deeper, and more interesting than the models we had built to describe it. The most important discoveries in physics have never been the ones that confirmed what we expected. They have always been the ones that didn't. If you found this video valuable, hitting the like button genuinely helps it reach more people. Subscribe so you don't miss the next one.